Lesson on polynomial functions. By the end of this video, you will be able to define a polynomial function, describe its key features like end behavior, and identify local and global extrema and concavity. Our main topic today is exploring polynomial functions and their rates of change. First, let's start with the basic definition. What is a polynomial function? A polynomial function can be written in this general form. This formula might look complex, but let's break it down. First, an represents the coefficients. These are real numbers that multiply each term. You can see these coefficients are all real numbers. The next key part is n, which stands for the exponents of x. The crucial condition for a polynomial is that all the exponents must be positive integers. This means you'll only have whole numbers like 1, 2, 3, and so on. You won't find negative exponents or fractions. Finally, the very first coefficient, an, cannot be 0. This ensures that the term with the highest power of x actually exists. This term, anxin, has some special names. The exponent n is called the degree of the polynomial. It's the highest exponent in the entire expression. The degree is simply the largest exponent you see. The term itself, nxln, is called the leading term, and the coefficient, an, is the leading coefficient. The leading term and leading coefficient are determined by this highest powered term. A special case of a polynomial is a constant function like y equals 5. This is also a polynomial. We can write it as p of x equals 5 times x to the power of 0, because x to the 0 is 1. Since the highest exponent is 0, a constant function has a degree of 0. Let's look at a few examples. First, p of x equals 3x squared minus 2x plus 1. Here, the highest exponent is 2, so its degree is 2. The leading term is 3x squared, and the leading coefficient is 3. As you can see, the highest power is 2. The term that contains it is 3x squared, and the number multiplying it is 3. Next, let's consider p of x equals 7x to the 5th power. In this case, the highest exponent is 5. Therefore, the degree is 5. The leading term is 7x to the 5th, and the leading coefficient is 7. The highest power is 5, so the degree is 5. The leading term is the entire expression, and the leading coefficient is 7. Finally, p of x equals 4 times the square root of x plus 6. We can rewrite the square root of x as x to the 1/2 power. The exponent 1/2 is not a positive integer. So, this function is not a polynomial. Because the exponent is a fraction, this function fails the definition of a polynomial. Now let's move on to the end behavior of polynomial functions. End behavior describes what happens to the graph as x gets very, very large in the positive or negative direction. We'll focus on the end behavior of the graph. The end behavior is determined by two things: the degree of the polynomial, which we call n, and the leading coefficient, an. There are two main cases to consider for the degree. We will first look at polynomials with an even degree. If the degree is an even number, like 2, 4, or 6, the graph's two ends will go in the same direction. That is, both ends will point upwards towards positive infinity, or both will point downwards towards negative infinity. For an even degree polynomial, both ends will always point in the same direction, either both up or both down. Whether they both go up or down depends on the leading coefficient, n. If the leading coefficient is positive, both ends go up. The function has a global minimum, a lowest point it never goes below. Think of a parabola, which is a degree 2 polynomial with a positive leading coefficient. It opens upwards and has a lowest point, a global minimum. This graph illustrates a global minimum at the bottom of the parabola. On the other hand, if the leading coefficient is negative, both ends go down. This polynomial has a global maximum, a highest point. This is like an upside-down parabola. Both ends point down, and there's a highest point, a global maximum. This graph shows a global maximum at the top. Now let's look at the second case for end behavior. What happens when the degree is an odd number? If the degree is an odd number, like 1, 3, or 5, the graph's two ends will go in opposite directions. One end will go up, and the other will go down. So for an odd degree polynomial, one end goes up and the other goes down. This means there will be no global maximum or global minimum for an odd degree polynomial, because the graph stretches infinitely in both the positive and negative y directions. A key takeaway is that odd degree polynomials never have a global maximum or minimum. Again, the leading coefficient determines the exact orientation. If the leading coefficient is positive, the left end points down and the right end points up. It rises from left to right. Think of a simple line, which is a degree 1 polynomial with a positive slope. It goes down on the left and up on the right. As x goes to negative infinity, p of x goes to negative infinity, and as x goes to positive infinity, p of x goes to positive infinity. If the leading coefficient is negative, the orientation is reversed. The left end goes up and the right end goes down. It falls from left to right. In this case, as x goes to negative infinity, the function goes to positive infinity, and as x goes to positive infinity, the function goes to negative infinity. Let's put this into practice. Let's describe the end behavior of the polynomial p of x equals 2x cubed minus 5x squared plus 3. We'll analyze the function p of x equals 2x cubed minus 5x squared plus 3. First, we need to find the degree and the leading coefficient. The highest exponent is 3, so the degree n is 3. The leading coefficient, an, is positive 2. So we have an odd degree and a positive leading coefficient. An odd degree tells us the ends go in opposite directions. A positive leading coefficient tells us the right end goes up. Therefore, the left end must go down. This means that as x approaches positive infinity, p of x also approaches positive infinity. In limit notation, we write that the limit as x approaches infinity of p of x equals infinity, and as x approaches negative infinity, p of x approaches negative infinity, and the limit as x approaches negative infinity of p of x equals negative infinity. So the end behavior is the same as the simple function y equals 2x cubed, rising from left to right. Next, let's explore turning points, also known as local maxima and minima. These are the peaks and valleys on the graph of a polynomial. We're now looking at turning points and extrema. A local maximum occurs when the function is increasing on one side and then decreases. It's a peak, but not necessarily the highest point on the entire graph. So a local max is a peak where the graph turns from going up to going down. Similarly, a local minimum occurs when the function decreases and then increases. It's a valley. A local min is a valley where the graph turns from going down to going up. Together, these local maxima and minima are called local extrema. Turning points and local extrema are interchangeable terms. A fundamental property of polynomial functions is that a polynomial of degree n can have at most n-1 turning points. This gives us an upper limit on how wavy the graph can be. It can have fewer than n-1, but never more. For example, a polynomial of degree 4 can have at most 3 turning points. There's also a relationship between turning points and the x-intercepts, or real zeros, of a polynomial. The property states that between every 2 distinct real zeros, a polynomial function has at least 1 turning point. Let's repeat that. Between any 2 places where the graph crosses the x-axis, there must be a local maximum or a local minimum. Why is this true? Imagine the graph crosses the x-axis, which is y equals 0. For it to cross the x-axis again at a different point, it must first change direction. If it was increasing, it must decrease to cross the axis again. This creates a local maximum. If it was decreasing, it must increase, creating a local minimum. Let's see this with a sketch. Imagine 2 zeros, C1 and C2. Here are 2 points on the x-axis. If the function's value is 0 at C1 and C2, and it goes up between them, it must come back down, forming a local max. You see that peak? That's our turning point. If it goes down between them, it must come back up, forming a local min. This property guarantees a turning point between any 2 x-intercepts, and here a local minimum. Our final topic is concavity and inflection points. Concavity describes the curve's direction, and it's related to the rate of change of the slope. Let's explore concavity and inflection points. Think of it this way. Concave up means the curve is smiling, and concave down means the curve is frowning. Concave up is like a U-shape. More technically, a function is concave up if its rate of change is increasing. The graph gets steeper as you move from left to right. This means the slope is increasing. Look at how the tangent lines get steeper as we move right. In calculus terms, this means the second derivative is positive. That's a concept you'll see later. Conversely, concave down is like an upside-down U-shape. A function is concave down if its rate of change is decreasing. The graph gets flatter as you move from left to right. The slope is decreasing. Notice how these tangent lines get flatter as we move right. The point where a graph changes from concave up to concave down, or vice versa, is called an inflection point. An inflection point is where the concavity changes. At an inflection point, the rate of change is not increasing or decreasing. It has a local maximum or local minimum slope. Think of it as the bend in the curve where it flips its curvature. In the graph of y equals x cubed, the origin, 0 equals 0, is an inflection point. To the left, it's concave down. To the right, it's concave up. The origin is the transition point. Let's summarize the key features we've covered today. Understanding how to find these features is essential for analyzing and sketching the graph of any polynomial function. Here's a quick summary table. First, the end behavior, which tells us the direction of the ends of the graph, is determined by the polynomial's degree and leading coefficient. Second, the number of turning points, or local extrema, is at most n-1, where n is the degree. Third, the property that between any two real zeros, there must be at least one turning point. Finally, inflection points are the locations where a polynomial's concavity changes. These are points of special significance. These concepts provide a powerful framework for understanding the behavior of polynomial functions. By applying them, you can build a strong foundation for more advanced topics in algebra and calculus. Thanks for watching.